Good morning, friends and dear students. I welcome you all here for my course, Engineering Thermodynamics. As of now, I have covered basic concept of thermodynamics, different types of properties, steam, pressure, temperature, specific volume, enthalpy, steam tables, zeroth law of thermodynamics, and thermometry. Today I am going to take some example problems and exercises, and this I am starting today and hope this will be very interesting and very useful for all the students of thermodynamics. So I am going to take today some 3 problems and I will try to solve these problems. So in today's I am going to discuss about problem 1, piston cylinder problem with stop. Then next problem is piston cylinder problem with spring, and problem number 3, piston cylinder problem with free spring. So what happens if one piston is filled with some gas and some heat or some temperature is increased by adding the heat, or the temperature is decreased inside the cylinder, then what will happen to the piston? If you give the heat, the energy will be increasing inside the piston and the piston will try to move up. So the first problem is related to that if there is a substance inside the cylinder and above is the piston and you heat it or you give some extra temperature, it will go up. So it will go up to what distance it will go up? There is a stop, whether this stop is reaching up to stop or not. So this is the problem for the today. So here the first problem, it is to be read nicely, that problem number 1, and it is 1.1. It is taken from my reference 1. This problem is taken from reference 1. So I will read out this problem and then I will discuss this issue and we will solve very closely. So problem 1.1, a cylinder has a thick piston initially held by a pin as shown in the figure. So this you can see here, this is the piston here, this is the piston, and this is here we have the pin. So a cylinder has a thick piston. Just you can see it is the size of this, height of this piston is 100 millimeter. It is shown in this diagram, and below is the CO2 and this green is your system. This is the piston and this is the atmosphere here. It is open. So a cylinder has a thick piston initially held by a pin as shown in this diagram. The cylinder contains this cylinder here. This is the cylinder. Cylinder contains carbon dioxide, that is the CO2 here as shown here. This is the CO2 at 150 kilopascal. So here the pressure is 150 kilopascal. This is and ambient temperature of 290 Kelvin, and temperature is 290 Kelvin, and this is the ambient temperature, means not more temperature. The metal piston has a density of 8000 kg per meter cube. So density of the piston is given 8000 kg per meter cube, and the atmospheric pressure is 101 kilopascal. So here 101 kilopascal. This is the atmospheric pressure. So it is P naught. The pin is now removed. So after this condition, we have removed this pin out, allowing the piston to move. And if you remove, piston will move either up or the down. We are not sure now in which direction it will move. And after a while, the gas returns to ambient temperature. So after this removing this, the gas again reaches to its ambient temperature of 290 Kelvin. So here is also same, and after it is reaching here, it is also same. So this T1 is also is equal to T stop. It is equal to 290 Kelvin. Is the piston against the stop? Is the piston will touch this stop or not? Or it is forcing this stop? This is the stop here. So whether your piston after this configuration, the piston is hitting this stop or not. So this is the question. So the answer I have shown here, that P2 is less than P of CO2. Hence, the piston cannot hold against the stop. So here, the pressure of this area is less than this pressure of this. This we will be discussing, and we will see that how we can go about. So now, here is the solution. The state 1, which is here, this is here state 1. So first we have to draw the diagram. I have here shown the same diagram in my hand drawing, maybe very poor. Here is this is the pin. This is the stop here. This is the piston. The height of the piston is this much, and this is from here to here is 100. This is here to here 100 millimeter, and from here to here is a 50 millimeter. So we have to find out that whether in this condition this is hitting this or not. So how we will find out? If the pressure of this is more than the pressure of this acting on the piston. So if this pressure, the piston pressure is lower than this, then it will hit. And if this piston is higher than this, it will not hit. Somewhere it will stop before that. So that is the objective of our this thing. So before we start, we should go with a free body diagram. So here, this you can see that state 1, P1 is equal to 150 kilopascal, and T1 is given 290 Kelvin. The density of the piston, that is given 8000 kg per meter cube. Atmospheric pressure is 101 kilopascal. That is the atmospheric pressure here. 101 kPa is given here. It is a P naught. And after that, this T here and this are same. That is the condition which is given. So now we need to draw the free body diagram of the piston for equilibrium. For equilibrium, the resultant forces on the piston should be 0. That is the condition for the equilibrium. So we will draw here. This is the piston here. This is the piston. The mass of the piston is MP, and this mass into G is equal to weight. And this weight will act bottom towards the lower side. Upper side, if you see here, this is the atmospheric pressure, P naught. So atmospheric, here is atmospheric. Atmospheric pressure is acting on top of this, and the pressure of this atmosphere is P naught, and the total force acting on the upper surface is force into area. The area of this from here to here. This is the area. It is a pi by 4 d square. So here P naught into A. And this CO2 is acting here. Here we see that it is P equilibrium. So we have to find out what is the P equilibrium. So in this case, this P equilibrium will act towards the downward side. So this downward side force, P equilibrium A, should be equal to the upper surface force, which is acting downwards, and the weight of the piston, which is also acting on the downwards. So by the principle of equilibrium, we can find out that P equilibrium A is equal to P naught A, which is upper surface of the piston where the atmospheric pressure is acting, P naught A plus mpg. This is the weight of the piston. So now we will divide by A. So this A is cancelled. So P equilibrium is equal to P naught plus mpg divided by A. Now we know that mpg is what? mp is equal to rho ah, means density. This is the density, and ah is a volume of the piston. So density into volume is a mass. So this mass mp is equal to rho pah. So rho pah into g divided by a. So a is cancelled. So here we will get P equilibrium is equal to P naught plus rho P plus height into G. And we have given here 101 is equal to P naught is equal to 101. It is given here P naught 101 plus density is equal to 8000. Then this height of the piston is 100 millimeter. So what is the H here? 100 millimeter or 0.1 meter. So here 0.1 here into 9.8. If you multiply this, you will get P equilibrium is equal to 108.8 kilopascal. So this we got one very important thing, that this P equilibrium means the force which is pushing upward is equal to P equilibrium. So means this much force it is acting upwards. Net force on the piston is 101.8 kilopascal upward. That we have to, from here onwards we will see that up to what distance it will able to travel. So that is the next issue, which whether it is acting or not. So we can see that here this P equilibrium, this P1 which is inside this chamber, it is given in the problem as 150 kilopascal, 150 kPa, but P equilibrium is 108.8. So now we have to see that how we can go ahead. So this P1 which is 150 kilopascal, so the piston want to go upward because this pressure is more than this, go up. So if we remove this pin and this, but the pin is making sure that it is in one place, but if we remove this, when pin is removed, the piston will have tendency to go upward. Oh, because in this system we have more pressure than the net equilibrium here. So this piston will try to go upward. As PQ is less than, so here we can see that this P equilibrium is less than the P1. It means this P equilibrium is 108.8, which is less than the 150 kPa. So what will happen? This is the tendency to move upward. Now we have to find out the other status, whether it is hitting or not. So we know that by the state equation, I will use here the state equation, and you will see that the state equation is P1 V1 by T1 is equal to P stop into V stop by T stop. But in the problem it is given that temperature comes back to atmosphere. So this T1 is equal to T stop. So this and this cancel. So we will get here P1 V1 is equal to P stop into V stop. This we got here. So we can find that now the P stop is equal to P1 V1 by V stop. P1 V1 by V stop. So we can see that now that V1 by V stop, V1 by V stop, so is equal to 100 by 150. By the diagram, V1 is equal to 100 and this is 100 plus upper side. If you see this diagram here, piston is here. So this is 100 and here is a 50 from here to here. So from here to here, piston has to move 150 millimeter. So 100 by 150. So we will get that. So here we will get P stop is equal to P1 into V1 by V stop. P1 is given as 150 into 100 by 150. So this cancel. So we got 100 kilopascal. So this P stop is 100 kilopascal. So we got here P stop is equal to 100 kPa. So this we got here. But we know that the final pressure which we got, that is the P stop, is pressure, it should be final pressure, it should be greater than or equal to P equilibrium. So here we see that P pressure is less than P equilibrium. So this stop here, this is here, it is less than the P equilibrium. We got 100 and 100 is less than the 108.8. So the piston will not hit the stop. So that is the answer, and this I think it will be very much clear that the piston will not hit, because I will again explain from my previous diagram here. We have seen that the P stop which we have got here, which is moving upward, is only 100 because it is moving. So this volume is increasing, so pressure is decreasing. From 108, it has become 100 here. But it can only touch when it is more than this. But the P equivalent is more than the P100. So this piston will not reach to the stop, and before that only somewhere here it will stop. So that is the question was asked here. Is the piston against the stop? So answer is no, as PR is less than the P. Okay, so it is 100 and it is less than 108.8. So not hit. Answer is not hit. So that is the problem, and hope this you might have got very well tuned. Now I will go for the second problem, and this you can see here that problem 1.2. This problem is related to the spring, and we know that spring, when we put it, give the linear effect. The variation of the parameters, thermodynamic parameters, will be linear. That is the indication of the spring. And spring is touching means it is giving some pressure or force on this piston. And here just I will read out this problem. So this you can see here that a cylinder is fitted with a 10 centimeter diameter piston that is restrained by a linear spring, force proportional to distance as shown in figure below. So here linear spring, that we have to take care of, that it is a linear spring. Here the force is proportional to the distance. F is directly proportional to the x, means the deflection of the spring as shown in the figure. The spring force constant is 80 kilonewton per meter, means spring constant K is 80 kilonewton per meter, and the piston initially rests on the stop. So here is the stop. This you can see here. These are the stops. This is the spring. This is the cylinder. This is the piston. And it is directly proportional to x. It is given. And with a cylinder volume of 1 liter, so volume 80 kilo, spring force is 80 kilonewton per meter. The cylinder volume is given 1 liter. We have to convert this liter into meter cube. So 10 to the power minus 3 we have to multiply. The valve to the air line is opened and the piston begins to rise. So this is the valve, and here is we have the high pressure. High pressure is flowing, and if you open this valve, air will enter inside this. Piston begins to rise when the cylinder pressure is 150 kPa. This will only start rising when the pressure is 150 kilopascal. When the valve is closed, the cylinder volume is 1.5 liter and the temperature is 80 degrees centigrade. What mass of air is inside the cylinder? So we have to find out the mass of air inside the cylinder. So this we have to find out. So a very interesting issue and very practical problem. I will be trying to give you always some practical problems, not just like that. So here also a pipe is there. From the pipe, air is moving. There is on top, there is a cylinder. If you open this valve, air will enter into the cylinder. On the top of the air, there is a stop. In the stop, the one piston is resting and it is pressed by the spring. So that is the problem, and whether this will move up or not, and how much mass of air is required to make this thing equilibrium. So that is the topic, and so I will just start here. So here we can find that the given data, what are the parameters are given here. So diameter of the piston, dia of piston, or I will write dp, is equal to 10 centimeter. We can make it as a 10 into 10 to the power minus 2 meter. Spring constant. Next thing is given spring constant K. This is given 80 kilonewton per meter. Volume, total volume at state 1, that is called V1, is equal to 1 liter. This we have to make in meter cube. So this is the meter cube. So equilibrium pressure at which piston starts raising. This is 1.5 liter, 1.5 into 10 to the power minus meter cube. T2, so this is the V2, state 2. This is the state 1. T2 is given 80 degrees centigrade. So we have to find out M2. What is the mass? This is our problem. So now I will draw one from same problem here. So this is our cylinder. There is a stop here. Piston is resting on top of this stop. This is the piston, and this piston has got on top of this there is a spring. This spring is pressing this piston. So here is your system. So here is your system. I am writing, just putting the dotted line, and your system is air. Flow of air is coming with some high pressure and entering and leaving. There is a valve. This valve will give some supply of air as and when it is required. So question is, how much mass will be mass of air in this? So now we have to, draw free body diagram of the piston. What are the forces acting on the piston? So I will just draw here the piston here. This is the piston, and from the bottom you will get equilibrium pressure. I will write as a P equilibrium into A, and this spring here, this is a spring constant, it is a Kx, because spring as and when it is pushing it will press down. Okay, and here is the atmospheric pressure. Here is the atmospheric pressure, and this P naught A, and here P equilibrium A, here is the Kx. Here we can neglect the mass of the piston, because we will take the difference, and in that difference it will be neglected. So here we can see that piston has a tendency to go up to spring, will give the downward force. So here the tendency of the piston will always be going upward, because here you have the pressure. So the spring spring will be pressing like this. So kx direction as shown in this. So now for equilibrium condition, P equilibrium, this force is equal to P naught A plus Kx. If we consider the mass of the piston, mpg. Also you can keep. But here I am neglecting because this mass will be cancelled out, that you can see later on. So now here P equilibrium is equal to P naught plus Kx divided by A. So now if we make the difference between P equilibrium 2 minus P equilibrium 1 is equal to Ka, because this P will also cancel, P naught will also cancel. So you will get K x2 minus x1 by A. So here we can make it as a K V2 minus V1 divided by A square, because we know this x is equal to V by A. So x1 is equal to V1 by A, x2 is equal to V2 by A. So here K V2 minus V1 by A, and A, this will be A square. So P, we will get here P EQ2 is equal to P EQ1 plus K V2 minus V1 by A square. So this we have got one equation for a equilibrium state at state 2. Now if we see here that how we can go about. So now we know that P equilibrium by the state equation, P equilibrium 2 into volume 2 is equal to M2 RT2, because we want to find out, so it is a state equation. And for low pressure and high temperature, we can consider that the air is ideal gas. So here if you see R, so what is the R? R is equal to specific gas constant, and this specific gas constant for air, its value is 0.287 kilojoule per kg Kelvin. This is the fixed value. But we know that this R is equal to, specific is equal to universal gas constant Ru by molecular weight. So we should not confuse this Ru. Here it is not Ru, it is a Ru by M. Here we have M is a molar mass. So we should put the specific gas constant, not the universal gas constant. So here PQE2 into V2 is equal to PM2RT2. So here T2 is equal to given 80 degrees centigrade. So plus 273.15. So this will be the T2 value. So we know here PQE2, we know the V2, all we know the R, we know the T2. So we can get M2 is equal to PEQ2 into V2 divided by RT2. So here if you put these values of all these parameters, V2 is already given, and PEQ2 just now we have got here PEQ2. We can find out from here PQE2 is equal to PE1 plus KV2 is given here, V1 is given, V2 is given, T2 is given. So everything is given here. So we can find out very well the PEQ2, and from PEQ2 means state 2 pressure, here PEQ2 we have find out. Okay, so here this you can do your exercise and you will get M2 is equal to 0.012 kg. So here this 0.287 into here 353.15, and V2 is already given here. V2 is equal to 1.5 into 10 to the power 3. So 1.5 into 10 to the power minus 3, and this EQ2 you can calculate from here by PEQ1 plus it is already given here. So in this way we can get this, the mass of the substance we can get. So this is my problem number 2 which we have done it. So I will go for my next problem, that is the problem number 3, and this problem number 3 relates to the spring which is not touching. In the previous case the spring was touching, but in this case spring is away, your piston will lift up, and this piston whether it is touching the spring or not, so that we have to see it by this problem. I am just reading this problem. A cylinder piston arrangement contains water at 105 degrees centigrade, 85% quality. Here we have to take very much care because it is a two-phase system. Because here the quality 85 means if it is 100, it is a dry saturated air, dry saturated vapor. But here is 85%, it is not dry, that I will be discussing in this our solution of the problem, with a volume of 1 liter. So state 1 is given, T is given, V is given. The system is heated, causing the piston to rise and encounter a linear spring as shown in the diagram. So here is this is the spring and it is given linear spring. Linear spring means F is equal to Kx. This is given. This is here piston. This is here cylinder. This is filled with water. But water is not pure liquid. It is a mixture of vapor and the liquid. It is in the two-phase system. As per the given quality is 85%. Initially it was 1 liter. As the piston is heated here if you give some heat here, if you heat this piston, now the volume is increased from 1 liter to 1.5 liter and the piston diameter is 150. This dP is 150 millimeter and the spring constant K is 100 Newton per millimeter. The heating continues, so the piston compresses the spring. So it will be heating till the time spring is hitting and it is compressing. So it means as it is touching, the pressure, the volume will remain constant, but pressure will be increasing. What is the cylinder pressure when the temperature reaches to the 600 degrees centigrade? So we have to find out the pressure when the temperature of this cylinder is reaching to 600 degrees centigrade. I have given the answer. The pressure is 193 kilopascal. This we have to find out by our solution of the problem. So here I will draw one state diagram again. The same type of diagram I can draw it here, and This we can see that here is the piston. This is the piston here. Here is the spring, and spring is not touching initially. Here is the your system, and the system is a water. So this is the piston, this is the spring, this is the cylinder, and here is the system is your water. So this is the configuration of our problem, and we want that what is the final pressure of the system. So here it is given T1 is equal to 105 degrees centigrade, quality X is equal to 85%, volume V1 is equal to 1 liter, 1 into 10 to the power minus 3 meter cube. State, this is the state 1. For state 2, we have V2 is equal to 1.5 liter, 1.5 into 10 to the power minus 3 meter cube. So, diameter of the piston dP is given as a 150 millimeter, and spring constant K is equal to 150 Newton per millimeter. So we have to find out the P3. So what is the P3? Find P3. State 3 we have to find out. So I will draw one PV diagram here. P and V diagram, and we can see that this is the one, and as per the problem, the pressure is constant up to 2. So this is the 2, and from the 2 means this is your 2. As it is touching this, your pressure will not be constant because it is a quasi state. Up to 1 to 2 it will be okay, but as it is touching the spring spring will push, but pressure will make upward. So this is your state 3. So we got this state, and 1 to 2 is a constant pressure, and 2 to 3 is not the constant pressure, as in this phase will change. So if you see here like this, so we have to represent in PV or the TV diagram. It will be better if we represent in PV diagram. It gives visualization what type of the process and how these things are proceeding ahead. So state 1 is in 2 phase, and it is given in the process pressure at 105 degrees centigrade temperature. So from the steam table, we have to use the steam table at state 1 to 2. State 1 is in 2 phase region, as X is equal to 85% and 105 degrees centigrade. So we have to see by the steam table. So from the steam table, the state 1 to 2 volume increases, but P is constant. This you can see here. 2 to 3, state 2 to 3, spring encounters 2, 3. So we have to draw a free body diagram, that is called FBD, free body diagram. So this we can see that how the free body diagram we can draw. So now we will see, I will draw the free body diagram of this system, and you will see that as we have done previously. This is the piston. Here we will see that this is the atmospheric pressure, and we are representing by P naught into area A of the piston, and from this side equilibrium pressure it will act, and we are writing as a P A or P equilibrium A. So here is a spring is there. So spring is Kx, and the mass of this thing will also act as a MP into G. So we can see here by the equation of equilibrium, the downward forces is equal to upward forces. So spring apply force in downward direction. So Kx here is in downwards direction. So spring apply the force in downward direction. So Kx is in this direction. So P into A is equal to P naught A plus MP into G plus Kx. So P is equal to P naught plus MPG by A plus Kx by A. Here this X is spring constant. Okay, so that we have to take care of, that it is a spring constant. So now if we make the difference, P3 minus P2 is equal to K, because this will be cancelled and this will be cancelled, because these are the same quantities, K into X3 minus X2 divided by A. This we can write as we have done in the previous. It is a K volume of 3 minus volume of 2 divided by A square. As we know that X3 minus X2 is equal to V3 minus V2 by A. So this, if you put this, A will become A square. So now at state 1, what is the condition? If you see here, PV diagram, state 1 is somewhere here. This is the state 1. So it is not here or here. So we have to find out exact specific volume of state 1. So this state 1, V1, we know that this is the VF, this is the VG, this saturation. So this V1 is equal to X1 VG1 plus 1 minus X1 VF1. So this X1 is given 85%. So we can get here that VF1 plus X1 VFG1. So from the steam table, we can find out this VF1. It is given, VFG is given, X1 is also given. We can find this V1. We can get from steam table. Okay, so and also we can get the area is equal to pi d square by 4. D is given here. We can find out this. So we know that the at 105 degrees centigrade we can find the U1 V1 from the table. So we know that mass is equal to m. This is equal to V1 by total V1 is given, and this is the V1. So we can get this P3. P3 is equal to A plus B V3. So we can make this thing, and at T3 we have 600 degrees centigrade. This is given. So we can find out the from this P3 we can get the V3. So P3 we will get 193 kilopascal. This is the answer. This calculations are very simple. This you can do. If I start doing, it will take a lot of time. So I try to avoid this calculation. I hope this will be okay. These are the references which I have taken this problem from this reference 1, and this also solved by NPTEL lecture. So you can find out this. Any questions you are welcome to ask. It will be my pleasure to reply. Hope this will be very useful for you all. I will also continue the next class also related to the problem solving part 2, some more advanced problems. And you know that my all problems are practically oriented problems. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.